All right, switching over to a bit of moving and shaking of a few buildings. And before I go there, the chair that Abe designed, our TDI director liked it so much, it's going to be our director's chair from now on. So myself, Ari Sinha, Tanner Field, here's the bright and upcoming PhD student. We'll talk about the Nehiri Converging Design project that involved a shake table test down at UC San Diego. We have a lot of PIs and co-PIs. They're all listed there. I'm not going to name them because that'll eat away our 7 minutes. And we have an army of graduate students, postdocs, as well as undergraduate students working with us in the project, as well as on site. It's a collaborative project between four different universities: OSU, Stanford, Colorado State University, and Penn State. And it's a perfect example of public-private partnership. We got funding from National Science Foundation, USDA ARS, and then Simpson Strong Tie generously provided a lot of funding. So did Core Brace, Boise Cascade, Ferris Lumber, to name a few, but there are other that mentioned at the end of the presentation. So the motivation for this work is to look at functional recovery. So we design buildings which are quite safe during earthquake, but after the event, there are irreparable damages because life safety has been our goal. So we need to do something about make these buildings more functional or the time to recovery minimal after an earthquake event. And that's why this converging design philosophy came into effect, and we went ahead and tested that converging design philosophy in the UC San Diego shake table for characterizing seismic performance and also looking at the time to repair and how repairs are being done. Now, this project cannot be viewed in isolation. This has been a team effort because we were taking over from a very comprehensive project led by Colorado School of Mines. Schilling Pei was the lead on that, and a lot of universities were involved for the 10-story building that was put to dynamic tests on the shake table at UC San Diego before us. But even before that, we didn't want to put a 10-story building right on the shake table. So we had a precursor to that in 2017 where the seeds were planted. We did a 2-story building test. Again, NSF and USDA ARS came together, funded that project. We got a lot of information. Then through the USDA ARS funded project at the Emerson Lab, which internally we call it the Emerson Lab Launch Initiative. It's called the ELI. We tested a 3-story building. We don't have the shake table capacities, but we did go back and forth from there. And then from there on, we decided we'll do a 6-story building after the 10-story building. So we took the top 4 stories off, swapped the lateral force sensing system, and tested that. And now Tanner will take over and talk more about the testing project and some results from there.
Thank you, Ari. So all of the experimental tests that Ari was just mentioning, we can look at the design concept through this push-up toy where when we push on it and it deforms and then we move our finger away, it goes back to its original position. And so we did the same thing with these mass timber self-centering rocking walls where, again, we push on it and you take away the loads and it goes back to its original position. And there's 3 main concepts that work with this to combine. First is the unbonded post-tension rods, and then the shear keys at the base to keep the wall from sliding and make it actually rock. And then not pictured is also the energy dissipation that we will use, which will vary depending on which phase of the project we're on, but it allows us to have a better structural performance. And so we can't look at the Converging Design project without also starting off with the 10-story TallWood project. And so the design objectives of this were resilient performance, which is where the building can quickly resume its function after a large earthquake. And for this project, the structural system, the goal was having no damage at the design level earthquake and repairable damage at the maximum considered level earthquake. And then for both cases, having no residual drift. And on the bottom 3 stories, you can see that non-structural system. And the goal for that was having no damage for frequent earthquakes and then having a repairable damage at both the design and maximum considered level of earthquakes. And so the building had a variety of different mass timber wood products. Starting off, the north-south rocking walls had mass ply panels from Ferrez. The east-west rocking walls were cross-laminated timber from Smart Lam. Floors 1 and 2 were cross-laminated timber from Mass Timber Services, and Mass Timber Services also supplied the floors 3 and 4, which were glue laminated timber. Floors 5 and 6 were nail and dowel laminated timber, respectively, both from StructureCraft. And then floors 7 through 10 and the columns and the beams were all from Boise Cascade, and those are veneer laminated timber. And all of this was connected together by Simpson Strong Tie hardware. And of course, experimental testing. We had lots of instrumentation on there, over 750 channels of a variety of different sensor types. And we had to hand check each sensor before each test to make sure that nothing went bad, because obviously this is an outdoor shake table. And so weather does play a little bit of a factor, even though we were in San Diego. And of course, many more cables to go along with all those sensors. This is from the 10-story. By the end of the 6-story, this looked fantastic. But a series of payload tests were performed on the building from both the 10-story and their couple phases, and then also the 6 stories phases. And this ran from May, actually 2023 to April 2024, and added up to a total of 244 earthquakes. And so, like I mentioned, is that we can't look at the 10-story without going into the we can't look at the 6-story without going into the 10-story, because this was the first example of specimen reuse, where we again took the top 4 stories of the 10-story and essentially cut them off. And so here, that was what we considered phase 0, where we did the deconstruction. And then there's also 3 other phases of different lateral force resisting systems that we put into the structure. Phase 1 was a MPP wall that had this distributed energy dissipation on the far right, which are the U-shaped flexural plates. And we'll go into just a video response of the maximum considered earthquake. On the bottom right, you'll start to see the wall rock potentially. Yep, there we go. And then on the top right is the staircase. And then on the left is, of course, the full building. And this is a 1.6 times Northridge earthquake, which occurred in California in 1994. And then on the left in gray, you can see that non-structural system moving and those panels opening and closing, and that was intended. Then moving on to phase 2, we swapped out 2 of the walls in one direction and replace them with this concentrated energy dissipation system using buckling restrained braces at the first level. And so here's a response of the MCE for phase 2. As you can see, it's very loud. And then finally, going into phase 3, we swapped out that concentrated energy dissipation system with this resilient steel frame that utilized a combined moment resisting frame and concentric brace frame that had the yield link moment connection and the yield link brace connection, both supplied by Simpson Strong Tie. And so now we'll go into a video of this and I'll kind of describe a couple of what other things you're seeing. The orange plates on the side of the frame are the yield link brace connections, and those served as the primary energy dissipation system. And then secondary was those yield link moment connections that you can kind of see on the beams. And the goal of those was actually to keep the building plumb and centered after the shaking. So the main takeaways from all three phases of this project were that earthquake resilient tall wood buildings are possible, but they're also practical. And that these post-tension, self-centering rocking wall lateral systems are the key to keeping buildings plumb and resilient against these repetitive earthquake ground motions. And we also showed that a beam column gravity system that has been designed correctly can withstand 200 or more earthquakes without needing to be repaired. And that similarly, an appropriate planned and detailed non-structural and stair system can experience repairable damage at these maximum considered events, but still remain functional. And of course, like Ari mentioned, these large collaborative projects are not possible without very strong industry partnerships. So we'd like to thank and acknowledge all of the companies and all of the other academic collaborators that helped making this project possible. Thank you.